Right, in this video, I'm going to just touch on how to do a transformation to try to improve any model assumptions that may have been violated in a simple linear regression model. Okay, and so in the previous video, we kind of walked through that for this data set, when I have the simple linear regression model, yi equals beta naught plus beta 1 x sub I plus model error term for I equals 1 to, in this case I have 187 observations, that I was having a problem in my plot of when I plotted my residuals. I think that the plot kind of looked like there was a little bit of variability and then a lot of variability. Okay, so basically our homogeneous variance assumption was potentially being violated. Also, there may have been a relationship in our curve. There may have been like a relationship in the residuals versus x. And so that would potentially mean that the model is also misspecified. So when we're, thinking about doing transformations, there's lots of things that we can do to make this model potentially fit better and to make those assumptions. Remember what are our model assumptions? That the expected value of our error is 0, which means the model is correctly specified. That the variance of the model error is sigma squared, so it doesn't increase, right? It's the same variability. And then also these EIs are uncorrelated or independent, and also that these EIs are normally distributed. Okay, so we can try to do better by these assumptions by making some transformations on x and y. Okay, and before I start thinking about what transformations do I want to make, let's try to think through what are some possibilities. If you want to make a transformations on x, you would be in a situation where when you plot x and y, so your actual observed data, basically you're not seeing a linear line. Okay, you don't see something that the data is just randomly scattered around a linear line. Okay, if it was, then you would have no need for a transformation. But instead, maybe you see something where you're seeing a curve like this. Right? If you see a curve like this, then you might think, okay, maybe I should do a transformation where x, maybe use x star for the transform value, equals maybe the log of x, of your observed value. Or maybe you might think, okay, also the square root. Right? Either one of these, it's very similar, it has that type of curvature. If you were in a situation when you plotted x and y, if you saw something like this, okay, here's x and y, you might consider something like an x squared type. So where you do a transformation of x squared. Or you could use the exponent, or e to the power of x, right? exp, right? Another thing that you might see, okay, x and y, you might see downward slope like this, downward curvature. And that might be a good time to use a inverse function, so 1 over x. Or e to the negative x power, okay, which is 1 over e to the x. So, these are different ideas on transformations on x, and again, you're doing a transformation on x because you have the random variability of these plots, but they don't appear to be linear, right? Now, a transformation on y, so this is basically when you think that your model is misspecified. A transformation on y is when you think that there might be a problem with the constant variance assumption. Okay, so transformations on y transformation on y. This might be a situation where you have your data, and when you plot it, x and y, what you're seeing is like not very much variability here, and then much more variability up here, right? So it's kind of like that. A little bit of variability towards the beginning, and then a lot of variability towards the end. So that looks like a violation of that constant variability. So you may consider a transformation like the square root of y. Okay? If your plot looked like it had a lot of variability towards the beginning and then less towards the end, right, something like this, you may consider a transformation like the log transformation. Right? And then if it does appear to be linear, but maybe it's not very much and then a lot, right? But there's like a linear relationship. Okay, and then it's a lot. Then you might consider a transformation like 1 over y. Okay. Point being that the variability assumption is being violated, and that's why you will consider a transformation of y. And sometimes it's helpful to do transformations on both x and y. And selecting the correct transformation, it can be a bit of a artwork, meaning, you know, there's not necessarily a right answer, but you kind of have to look around and, you know, try different things. Though there are other methods of trying to pick the best transformation that we're not really going to dive into in this introductory course, but just know that there certainly are more complicated transformations than the ones that we're going to discuss here today. Okay, so first thing I want to do is go ahead and run that linear regression on my original data. Let me go up top, press data, data analysis, regression. All right, get my cursor there in that Y, highlight my data, and then go cursor to the X value, and then highlight the data, shift control, down arrow. Okay, I included the labels when I highlighted my data, and I'm going to output on a new workbook. I'm going to call that workbook maybe original data. I want to go ahead and get the residual plot and the line fit plot. And no need for the normal probability plot. So that's okay. So I'll press OK. All right. So this is the line fit plot. This is what I really want to look at right now. Well, I want to look at both of them, but okay. So this is our original data. What are we seeing here? We're seeing this cone, right? So it's wider here than it narrows in. So I'm thinking that a transformation on y is a good place to start. Okay, and since I have a lot of variability there in the beginning and then less towards the end, I'm thinking of using that log transformation. Okay, so I'm going to go back to my data. Let me scroll up, and actually I'm going to copy this, right click, press copy, and then go to a new sheet, press paste. Okay, I'm going to label this sheet data with transformations. Okay, so I have let me reorganize this. So I have data, original data, output, and then data with transformations. So let's call this one log y. And to find that, press the equal sign, type in log, open parentheses, and press that number. There we go. So this is the log of y. Get your cursor to look like that black cross, double click, and it'll find the log of all the y's. All right, so I'm going to go to data analysis, regression. Okay, you may have to clear out what's in there. Instead of y, now it's going to be log y. X range, that stays the same. I want to call this log y. Okay, press OK. All right, So let's see what we have here. Okay. So did that help? Did it help? Now our original, this is the plot of log y versus x. On the original data, right, if I were to delete my little, yeah, you see how there was much more variability in that curvature. Now that it's transformed, you're seeing that go away a little bit. So it definitely helped, but we still have definitely, maybe there's something going on here that's like curving these residuals. Okay, so that curvature of those residuals, you know, we may think, okay, you know what, maybe we should do some sort of transformation on x as well. Okay, let me move this here. So I've already transformed y, and it definitely helped. I can transform x as well. So let's go ahead and use the log transformation of x as well. So equals log, open parentheses, and then this guy, close parentheses, press enter, and then double click, fill it all in. Data analysis, regression, okay, y is going to stay the same. X is going to, let's delete that, and let's do our log x. All right, and log y and log x. Okay, press OK. And let's see what we're seeing here. So this is my plot. This is my residual plot. Right? And this is definitely I'm starting to see an improvement. What I want to see is just like a random scattering around this orange line, right? I'm definitely seeing some improvement, but it looks like there may be a few values that may be outliers. Okay, you see how these guys are potentially outliers, which is kind of shifting this line. So yeah, I might consider, you know, outlier detection, right? Looking for outliers, and then potentially, you know, outliers, just because they're outliers doesn't necessarily mean they should be removed from the data set. That's very important. Just because you have an outlier, I do not recommend, you know, just removing it. Rather, you know, think about why is it an outlier, and how you can best improve your model with that outlier there. Okay, so definitely we're starting to see that our model assumptions, though, are doing a much better job. Okay, and you know, I could do my probability plot, my normal probability plot, and see how that's doing as well. If I wanted to do that, I would go down here. We have here the predicted log value, and then we also have the residuals. So if I wanted to do a normal probability plot with these residuals, first thing I would do is find the semi-studentized residuals, and that's going to equal your residual divided by, looks like this is covering it. So let me just move this plot. Divided by the standard error of the model, which is right here. So this guy divided by this guy, lock that there, B7, press enter. Okay. So these are the semi-studentized residuals, and then I would need to find that z value, which I need to sort this data. So let me take that, and I want to go home and data sort, right? And I want to sort it by the residual value. Press OK. So now it's sorted by residuals. Let me reorder these observations. This is 1, 2, 3. Right, this is the rank of the sorted values. Just messed that up. Let me go back up here. Okay. Double click. Right, the rank of the sorted values. So z equals norm dot s dot inverse. Open parentheses. The numerator is the observation number. minus 0.375 divided by n, which is 187, right? The number of observations is 187, good, plus 0.25. Okay. So if I were to plot this, we go to Insert. So if I highlight the data, I think it helps with the plotting. There we go. Let's double check it did it right. Select Data, Edit. So X is X. I like X to be what Z is, so let's delete that. Actually, delete that. So X is the Z value. Oh, make sure you only highlight the number, okay? And then Y is the studentized residual. Scroll all the way back up. Starting here at the studentized residual. Don't highlight the label. It'll mess everything up. Okay. Okay. So it's saying the series name is at E24. So they're calling it just Z. Let me just call it normal probability plot. Okay. So I have E25. Good. E25. And then all the way to E211. That's the X value, these even numbers. And then Y is the studentized residuals, which goes from D25 all the way down. Okay, press OK. Looks good. Press OK. All right, so here we have our plot, and we see that it's doing a slightly better job than it was doing before, but we do still have, remember what we want it to be is slope 1, and it's a linear line, slope 1, and it goes through the intercepts, right? And we're definitely still seeing some divergence from that. So we could continue looking for other transformations to try to help us out with that, or we may consider, that we may have some outliers that are potentially affecting our distribution of the model errors terms. Though, based on this normal probability plot, I would very much be hesitant to interpret the p-values from our hypothesis test and to interpret the confidence intervals that the data analysis toolpath calculated for us. Anything that involves that normal probability assumption, it does appear like it is currently being violated, and we would have to definitely continue looking into this before we would be okay making those interpretations.